So, let's go. Quantum mechanics has been confirmed to 12 decimal places, powers every piece of technology you own, and after 100 years, nobody on Earth can tell you what it actually means. 7 paradoxes. Each one unsolved, each one stranger than the last. Number 1. The measurement problem. Quantum mechanics runs on 2 rules. Rule 1. When nobody's looking, a quantum system evolves smoothly, predictably, like a wave spreading through water. Rule 2. The instant you measure it, that wave snaps randomly into one definite outcome. A coin that was somehow both heads and tails suddenly picks one. Here's the bug. Rule 1 is smooth and reversible. Rule 2 is random and irreversible. They contradict each other. And the theory never tells you when to switch from one to the other. The word measurement appears in the equations like a magic spell. No definition, no mechanism, no explanation. The most successful theory in human history doesn't know what looking at something means, and it's not like physicists haven't tried. At the 2024 World Science Festival, Brian Greene asked 3 quantum specialists to explain this. He got 3 completely different answers. Because the problem is actually 3 problems stacked in a trench coat. First, why does measurement give you one outcome instead of a blur? Second, why does nature prefer certain kinds of outcomes over others? Third, where exactly is the line between the quantum world and the classical world? Where does weird stop and normal begin? Nobody has solved any of them. Now you might have heard of decoherence. It's the best attempt so far. Developed in the 80s, it explains beautifully why quantum weirdness becomes invisible at human scales. Interactions with the environment wash out the superposition. Great. But decoherence doesn't explain why you get this specific result instead of that one. It narrows the mystery. It doesn't close it. So the most fundamental process in quantum mechanics, the act of observing something, is the one thing the theory can't explain. Every paradox you're about to see is a symptom of this one unsolved bug, and it's been open for 100 years, which brings us somewhere stranger. Number 2, the quantum Zeno effect. You know the saying, a watched pot never boils? In quantum mechanics, that's not a saying. It's experimentally verified. If you measure a quantum system frequently enough to check whether it's still in its starting state, it gets stuck there. The system freezes. Not because you're interfering with it in some clumsy way. The math itself prevents the transition. The more often you look, the less anything changes. Look often enough, and nothing ever happens. This was first confirmed in 1990 at a lab in Boulder, Colorado. Physicists trapped beryllium ions and tried to drive them between 2 energy levels while simultaneously checking which level they were in. The more frequently they checked, the more the atoms refused to move. In 2024, a team in Sweden did something even more direct, 1 electron sitting between 2 quantum dots. Crank up the measurement strength and the electron locks in place. It cannot tunnel from one dot to the other. Observation pins it there like a butterfly under glass. And here's where it flips. Under slightly different conditions, frequent measurement doesn't freeze a system, it accelerates the decay. This is called the anti-Zeno effect. Whether watching freezes or hastens change depends entirely on how you watch. Observation isn't neutral, it's a lever, and it can push either direction. Now zoom out, the environment is constantly interacting with quantum systems everywhere. Photons bouncing off atoms, air molecules colliding. In some sense, the universe is measuring itself all the time. So a paper published in 2025 asked the obvious question, why isn't the universe frozen? The answer is unsettling. It's not that the Zeno effect can't freeze reality, it's that the environmental interactions happen to be too weak and too slow to trigger it. We got lucky. The universe works because the coupling strengths happen to fall in the right range. Not because of some deep law, because of an accident. If you could observe a uranium atom once every zeptosecond, that's 10 to the negative 21 seconds, the time it takes light to cross a single proton, you could prevent that atom from decaying. Its 4.5 billion year half-life would become infinite, not because you changed the atom, because you watched it. The first paradox was about what measurement does. This one is about what measurement prevents. The observer isn't just changing the system, they're holding it hostage. But at least with the Zeno effect, the strangeness stays local. The next paradox doesn't. Number 3, the EPR paradox. 1935. Einstein, along with Podolsky and Rosen, publishes a thought experiment designed to prove quantum mechanics is incomplete. Two particles interact, then fly apart. Quantum mechanics says measuring one particle's spin instantly determines the other particle's spin, no matter how far away it is. Instantly. Not at the speed of light. Instantly. Einstein says that's ridiculous. The information must have been baked in from the start, like two sealed envelopes, one containing a red card and one blue. You open one, you know the other. No spookiness needed. There must be hidden variables. Quantum mechanics just isn't showing us the full picture. For almost 30 years, this was a philosophical argument. Then, in 1964, a physicist named John Bell turned it into math. He proved that if those hidden variables exist and obey locality, meaning no faster-than-light influence, then the correlations between the two particles have a mathematical ceiling, a hard limit. And quantum mechanics predicts correlations above that limit. So now it's not philosophy, it's a testable prediction. The experiments started in the 70s. Every single one violated Bell's limit. Quantum mechanics was right, but there were loopholes. Maybe the detectors were influencing each other. Maybe the sample was biased. In 2015, 3 independent groups slammed those loopholes shut simultaneously. The most dramatic one used nitrogen atoms trapped in diamonds, separated by 1.3 kilometers. No wiggle room left. In 2022, the Nobel Prize went to the physicists who closed those loopholes. China's Misha satellite pushed it further. Bell tests across 1,200 kilometers. If some hidden signal is coordinating these particles, it's traveling at a minimum of 10,000 times the speed of light. But here's the thing. Nature gives you the weirdness for free, but charges for the message. Each individual measurement looks completely random. You can't use entanglement to send information faster than light. The correlations only appear after the fact when you compare notes. So nothing in relativity actually breaks, which means the paradox isn't really about spooky action at a distance. The real unsolved part is what Bell's theorem doesn't rule out. It kills local hidden variables. But it can't touch superdeterminism, the idea that the measurement settings themselves were predetermined at the Big Bang, that every choice you made during the experiment was baked into the initial conditions of the universe. And here's the problem. You can't design an experiment to test this because the experiment itself would be predetermined. If superdeterminism is true, every experiment in the history of science was rigged from the start. And there's no way to check. Now, so far the paradoxes have been about what happens when you look at things. The next one is about what happens between looks. Number 4, the tunneling time paradox. Imagine throwing a ball at a wall and watching it pass straight through. Not over, not around. Through. That's quantum tunneling. And it's not science fiction, it's happening inside your body right now. It powers the nuclear fusion in the sun. Protons in the sun's core don't have enough energy to overcome their electrical repulsion. Not even close. They're about 1,000 times too weak, but quantum tunneling lets them cheat. Each collision has roughly a 1 in 10 to the 28 chance of tunneling through. Absurdly small. But with 10 to the 38 collisions happening every second, the sun fuses 620 million tons of hydrogen per second. The star that keeps you alive runs on a quantum loophole. So tunneling is real. The paradox is, how long does it take? In 1962, a physicist named Thomas Hartmann showed something disturbing. The time delay for a particle tunneling through a barrier doesn't increase as the barrier gets wider. 1 nanometer thick or 1 meter thick, same delay. The implied speed exceeds the speed of light. In 2019, a team in Australia built what's called an attoclock, a rotating laser barrier, and measured tunneling delays in hydrogen atoms. The result? At most, 1.8 attoseconds. In that time, light travels about half a nanometer, the width of a single atom. Some headlines called it instantaneous. Then, in 2020, a team in Toronto tried a different approach. They cooled rubidium atoms to about 1 nanokelvin, barely above absolute zero, and sent them toward an optical barrier 1.3 microns thick. Using a technique called weak measurement, they clocked how long the atom spent inside the barrier. The answer, 0.61 milliseconds. Not instantaneous, but less time than it would take to cross the same distance in open space. The atoms moved faster inside the barrier than outside it. So which is it? Instantaneous, faster than light? faster than just really fast? In 2024, a unified theory using atomic clocks showed that there is no superluminal tunneling. The apparent paradox comes from forcing classical ideas about trajectories onto particles that don't have trajectories. The particle isn't moving through the barrier. It was never in one place to begin with. And then, in 2025, physicists found something even weirder: tunneling without a barrier. In certain laser field configurations, tunnel-like events happen at the exact moment the electric field hits zero. There's nothing to tunnel through. The barrier doesn't exist, and the particle tunnels anyway. 1 attosecond is to 1 second as 1 second is to 31.7 billion years, more than twice the age of the universe. That's the timescale we're talking about. You blink, and 300 quadrillion of these events could have happened. The question, how long does tunneling take, may not have an answer, not because we can't measure precisely enough. Because the question assumes the particle was somewhere, traveling somewhere, and in quantum mechanics it wasn't. We've broken measurement, we've broken time, let's break causality. Number 5, the delayed choice quantum eraser. You know the double slit experiment. Fire photons one at a time at 2 slits. They build an interference pattern, wave behavior, add a detector to see which slit each photon went through. The interference pattern vanishes. Particle behavior. Observing which path it took changes the outcome. Now here's where it gets dangerous. In 1978, John Wheeler proposed a twist. What if you delay the decision about whether to detect the path until after the photon has already passed through the slits? You'd think it shouldn't matter. The photon already went through. Too late to change anything. It matters. The delayed decision still determines whether interference appears. Wheeler imagined this at cosmic scales. Light from a distant quasar, gravitationally lensed by a galaxy, split into 2 paths billions of years ago. A decision you make on Earth today seemingly determines what that photon did before the Earth existed. Then, in 1999, a team built the full version. The delayed choice quantum eraser. Entangled photon pairs. The signal photon hits a detector first. The idler photon hits a second detector later, either preserving or erasing the which path information. The choice happens after the signal is already recorded. Now here's what most videos about this get wrong. Looking at the signal detector alone, you always see a smooth blob. Always. Not an interference pattern, not a particle pattern, a featureless smear. The interference pattern only shows up when you go back and sort the signal detections based on what happened to their idler partners. The pattern was always hidden in the data, overlaid with its opposite, the two canceling into noise. The idler measurement doesn't change the past, it tells you how to read it. A 2024 mathematical proof showed this rigorously. The delayed version and the non-delayed version produce the exact same final quantum state. At no point is information from the future needed. So no, the future doesn't change the past. But here's what's still unexplained. The correlations between the signal and idler photons are real, instantaneous, and have no classical explanation. A measurement on a distant photon determines whether a subset of your local data shows interference or not. That's not retrocausality. But it's not normal either. The information was never in one time or one place. It was smeared across entangled correlations that don't care about your idea of before and after. The future doesn't rewrite the past. But the present was never just the present. Now we scale up. Number 6. The black hole information paradox. Everything so far has been small. Photons, atoms, electrons. This one is about the most violent objects in the universe, and the stakes are the most fundamental rule in quantum mechanics. Here's the rule. Information cannot be destroyed. Ever. If you know the final state of a system and the laws that govern it, you can always work backward and figure out what the initial state was. Always. It's called unitarity. It's not optional. It's the foundation. In 1975, Stephen Hawking broke it. He showed that black holes emit radiation, not from inside the event horizon, but from just outside it, squeezed from the vacuum by the black hole's gravity. This radiation is thermal, random. It depends only on 3 things: the black hole's mass, spin, and charge. Nothing else. Throw a book into a black hole. Throw a planet. The radiation looks the same. And when the black hole eventually evaporates, which takes about 10 to the 67 years for a stellar mass hole, that's a number with 57 more zeros than the age of the universe. The information about everything that fell in is just gone. Quantum mechanics says that's impossible. General relativity says it happened. One of them is wrong. Hawking's own doctoral student, Don Page, proposed the test. If information survives, the entanglement entropy of the radiation should rise, peak around the halfway point of evaporation, then fall back to zero. A curve. The Page curve. Hawking's math shows the entropy rising forever, no curve, just a line going up into oblivion. Now here's where it stands as of right now. In 2019 and 2020, a group of physicists pulled off something nobody expected. Using a framework called quantum extremal surfaces and a concept called entanglement islands, they showed that even within semi-classical gravity, the Page curve can be recovered. Information is preserved. This was real, published, peer-reviewed physics, a genuine breakthrough. But what these islands actually are, mysterious regions inside the black hole that somehow contribute to the entropy of radiation on the outside, nobody can say. And that's where the hard science ends and the proposals begin. At a 50th anniversary conference in 2025, the field laid out its competing visions. One camp says black holes have no interior at all, that they're tangled balls of quantum strings called fuzzballs. Another says wormholes connect the radiation to the interior. Another says the information spawns off into baby universes we can't access. Another says space-time itself around the black hole is subtly entangled with what's inside, and next-generation gravitational wave detectors launching around 2035 might detect the signature, Leonard Susskind lectured. 50 years of debate spread across a room full of people who still disagree. In 2004, Hawking conceded a famous bet to physicist John Preskill and paid up with a baseball encyclopedia. But some physicists still think Hawking was right the first time. The Hawking radiation from a solar mass black hole has a temperature of about 60 nanokelvins. That's 100 million times colder than the cosmic microwave background. You'd need a thermometer more sensitive than anything that exists, and the information stored in a 10 solar mass black hole is about 10 to the 78 bits. The visible universe has about 10 to the 80 atoms. A black hole, the mass of a building, encodes more information than every book ever written. 50 years. Still no answer. But the last paradox is worse. Number 7, Wigner's friend. This is the one where quantum mechanics tries to describe itself and fails. 1961. A physicist named Eugene Wigner imagines the following. Your friend is in a sealed lab. They measure a quantum system, say a particle that's 50-50 spin up or spin down. They see a definite result. Spin up, done, settled. They know what happened. But you're outside the lab. And according to quantum mechanics, you have to treat everything inside that lab, the particle, the detector, your friend, their brain, their experience, as one quantum system. And from your perspective, it's still in superposition. Your friend is in a superposition of having seen spin up and having seen spin down. They haven't experienced one result. They've experienced both. And you're both using quantum mechanics correctly. So, who's right? Did your friend see a definite outcome, or are they smeared across two realities? Quantum mechanics gives two contradictory answers depending on whether you're inside or outside the lab. In 2018, two physicists at ETH Zurich made it worse. Daniela Frauchiger and Renato Renner built an extended version with 4 agents. Alice, Alice's friend, Bob, Bob's friend, all using quantum mechanics, all reasoning correctly. And they arrive at logically inconsistent predictions. One agent must conclude that another agent predicted the opposite outcome with certainty. A peer reviewer tried 5 times to find a mathematical error. Couldn't. In 2020, a team derived what they called local friendliness inequalities, mathematically similar to Bell's inequalities, and showed they're violated. Meaning at least one of 3 things must be false. Either the universe is superdetermined, or locality is wrong. Or there's no such thing as an objective observed event. What happened depends on who you ask, and neither answer is more real than the other, or real. In 2024, a stronger version was published. No post-selection needed, no workarounds. The contradiction is cleaner and harder to escape. And then in 2025, a paper proved that the black hole firewall paradox and the Wigner's friend paradox are the same paradox. The 2 biggest unsolved problems in physics aren't 2 problems, they're 1. So here are your options. Pick one. Quantum mechanics isn't universal. It works for photons and atoms, but breaks down for complex systems like human beings. Or, there are no objective facts. What happened in that lab depends on who's asking, and no perspective is more real than any other. Or, free will is an illusion. Every measurement, every choice, every experiment was predetermined at the Big Bang, and the question was never yours to ask. A physicist at Tel Aviv University called the experimental tests using photons as observers ridiculous. The friend has to be macroscopic, he said. A philosopher at NYU put it more bluntly. Nobody thinks a photon is an observer. To actually test this, you'd need to put a human-scale system into coherent quantum superposition. We can't do that. We might never be able to. So the deepest paradox in physics might be permanently out of reach. Not because the universe is hiding the answer, because the question is about us, and we can't put ourselves in the experiment. 7 paradoxes. All unsolved, all active, all connected. The measurement problem is the crack in the foundation. The Zeno effect shows observation holding reality hostage. Entanglement proves reality isn't local. Tunneling suggests particles were never anywhere. The quantum eraser shows information doesn't live in time the way you think. Black holes threaten to destroy information permanently. And Wigner's friend says the theory can't even describe the person using it. 100 years, the most successful theory ever built, and the birthday cake had 13 flavors. Nobody could agree which one they were eating.